Hey, it's Poisson Variance, your VTuber math lover gamer and nonsense enjoyer, and today we're going to be talking about second-order linear ODEs, or ordinary differential equations. Your general form of them can be written in the form of y double prime plus p of x y prime plus q of x y equals r of x. But today we're going to be looking specifically at homogeneous linear ODEs. These are in the form of y double prime plus p of x y prime plus q of x y equals 0. Now, the fundamental theorem of homogeneous linear ODEs lets us know that the general solution will be in the form of y of x equals c1 y1 of x plus c2 times y2 of x. When we have initial conditions, then we're able to actually find exact solutions. These solutions can end up in a few different forms. Let's take a look at 3 different examples. Before getting into the specifics of the first example, let's look at the most basic form of a homogeneous second-order linear ODE. It looks like this, where a, b, and c are real numbers. We can start by making a pretty fair assumption that y of x is equal to e to the power of lambda times x, where lambda is unknown. This gives us that y prime, its derivative, is equal to lambda times e to the lambda x, and y double prime is equal to lambda squared times e to the lambda x. This allows us to replace terms in the general equation to create the characteristic equation, namely a times lambda squared plus b times lambda plus c is equal to 0. Look familiar? It should. It's similar to a quadratic. Now let's take a look at that first example. So here's the ODE that we're going to try to solve, and here are our initial conditions. Set the initial conditions to the side for a minute, but for now, let's look at the ODE and plug in our y of x equals e to the lambda x. Just like in the general example, we can create the characteristic equation of lambda squared plus lambda minus 2 equals 0. Now we can solve for a lambda 1 and a lambda 2 the same way that we would solving a quadratic. This gives us that lambda 1 equals 1 and lambda 2 equals negative 2. Plugging in our y of 1 equals e to the lambda 1x and y of 2 equals e to the lambda 2x, we get the general solution of y equals c of 1 e to the x plus c2 e to the negative 2x. In this case, c and 1 and c2 are both unknown constants. That's how we utilize our initial conditions. By plugging in one of our initial conditions and then solving, we can find that c1 equals 4 minus c2. Our second initial condition requires the use of the derivative. So we take the derivative of the general solution. We can plug in both c1 equals 4 minus c2 and then solve for c2. This gets us that c of 2 equals 3. We go back and plug that into our original c1 equals 4 minus c2 to find that c1 is equal to 1. With both c1 and c2 known, we can finally get an exact solution. Y of x equals e to the x plus 3 times e to the negative 2x. In this example, we'll be looking at a solution where a characteristic equation has a double root. Let's go ahead and look at this example with these initial conditions. First up, same as last time, we set up our characteristic equation using y equals e to the lambda x and its subsequent derivative and double derivative. When solving for lambda, we get that lambda 1 and lambda 2 are both equal to negative 3. Now you may just think, oh, we can plug in lambda 1 and lambda 2 to our general solution. But because they're the same, we cannot. Our solutions of y1 and y2 must be linearly independent. In order to account for this, we would need to solve for another general solution that I'll leave to you. But here's the setup. Consider y double prime plus by prime plus cy equals 0. In this case, lambda 1 and lambda 2 are both equal to negative b over 2. This implies that y1 equals e to the negative b over 2 times x. Then, if we let y2 equals u of y1, where u is a function, we can go ahead and solve and figure out exactly why this works. But again, I'll leave that to you. Solving this gives that our solution when lambda 1 equals lambda 2 must be in the form of y of x equals c1 plus c2 times x, all times e to the lambda x. So, if we go back to our example, our solution would be in the form of y equals c1 plus c2 times x e to the negative 3x. Now, just like last time, we can go ahead and plug in our initial conditions. For the first one, we're able to find that c1 equals 1 pretty easily. Now, we take the derivative of our general solution y of x. Then when applying our second initial condition and plugging in that c1 is equal to 1, we get that c2 is equal to 6. Thus, our particular solution is y of x is equal to 1 plus 6x all times e to the negative 3x. We have one more case to look at, and that's the case of when we have complex roots. If you've worked with quadratics before, which, watching this, assuming you have, then you'll know that it's not uncommon to get roots that are complex numbers. Consider this ODE, y double prime plus 2y prime plus 4y equals 0 with the following initial conditions. Just like before, we get our characteristic equation and solve for lambda. In this case, lambda is equal to -1 plus or minus root 3 times I, which is definitely an unfriendly looking pair of roots. If we were to plug this into our general solution, we'd get the following, which looks even less friendly. But let's take a look at what form our components are in. If we utilize Euler's formula, this allows us to rewrite e to the beta I times x into cosine beta x plus I times sine beta x. If we break up our general solution a little bit and then plug that in, we can rewrite it as the following. Now, since cosine is an even function, i.e. f of negative x is equal to f of x, and sine is an odd function, f of negative x is equal to negative f of x, that means we can rewrite our general solution as the following. You may have noticed that we now have a capital A and a capital B. Because c1 and c2 are both arbitrary constants, we can rewrite c1 plus c2 as A, and c1 minus c2 as B. That's what leaves us with this general solution. Now let's go ahead and bring in our initial conditions as per usual. Plugging in our first one, we can find that a equals 0. Once again, we take our derivative and plug in our other initial condition to find that b is equal to 1 over the square root of 3 times I. Thus, our particular solution is y of x is equal to e to the negative x times 1 over root 3 sine root 3 of x. There we have it, the 3 cases of solving second-order homogeneous linear ODEs with constant coefficients. Quite a mouthful. Anyways, I've been Poisson Variance, your vtuber math lover gamer and nonsense enjoyer. Thanks for watching, I'll see you all next time. Bye bye!